All right, hello out there, folks. We're venturing on in our weathering unit here, right? We talked about physical weathering, then chemical weathering. And today we're going to talk about the rates of either type of those weathering, right? How quickly it happens, what can affect those rates, speed them up, slow them down, etc. Okay. As you can see here, a couple of cool pictures. Here you have rock that's worn unevenly. And that's because there's a different rate of weathering going on there. So we'll talk about the reasons why that might be. Here you can see clearly you have thicker rock on top, skinnier on the bottom. Why is that, right? There's a different rate of weathering there. And again, we're going to try to get to the bottom of that. So here we go. Beautiful artwork, right? Mother Nature is quite the carpentry person there. And you can see everything's sculpted. And again, it's different thicknesses and it seems to be weathering at different rates for some reason, right? This classic setting would be like out in the Midwest or the Southwest, like Utah area, Bryce Canyon, a lot of beautiful areas down that way, canyon lands. Okay, read this through, the factors that affect the rates of weathering. It runs through a couple of quick ones, right? So hit pause and please read that through. Okay. The big three factors, here they are, right? The surface area, the climate, and the mineral composition. So if you look at the top of the screen, surface area, you know, when we take a solid block and we break it into smaller pieces and break it into even more smaller pieces, you expose more of those surfaces to the atmosphere, and therefore you would speed up that rate of weathering. Okay? So that's a part of what's going on there, right? Of course, increasing surface area. And that's what this little activity is. Pretty easy to imagine. I'm sure you've all seen Alka-Seltzer or something dissolving. But if you take two Alka-Seltzer tablets, the same size, and you put them in the same size beaker of water, but one of them you break up into a powdered form, what's going to happen, right? How will that rate of weathering be affected? Well, what do you think? Powder, like before here, has a greater surface area, so should it weather faster or slower? And that's what this was all about. Okay, I'll show you a quick little clip here if you didn't figure it out on your own yet. Check it out. Here we go. Solid versus powdered. And clearly you can see the solid one dissolving, but the powdered one is pretty much dissolved already, right? There's no more bubbling going on. It kind of happened already, and that's because it's got a greater surface area, so the reaction happened a lot faster, and you can see the water clearing up as it's totally dissolved in the water, but this one is still dissolving, okay? So right there, without a doubt, having a greater surface area will change your rate of reaction. Get this up here. Okay. And of course, that greater surface area will speed that reaction up. So here we go. Taking that rock there, breaking it into smaller pieces, definitely will have an impact on rate. And there it is. Small particles, more surface area, faster weathering. Larger particles have less surface area and slower rates of weathering. Okay? Climate is also a big factor, right? Because climate is variations of temperature and moisture. And when you change those two things, well, that changes the rates of reactions. So clearly, if you have more moisture, we talked about that frost wedging scenario the other day, then over time, hang on one second there. Okay. Over time, the water freezes and expands, and you get this physical weathering going on. So if you have a climate that has a lot of water, well, maybe you're more prone to physical weathering. Here we have chemical weathering, looks like going on the statue, as well as some physical. And of course, different climates will affect that. So check it out. Warm, moist climates tend to have faster rates of weathering. Cold, moist climates tend to have more frost action, whereas the warmer one tends to have more chemical weathering. Right? Remember, frost action is physical weathering. But in either climate, the more rain you get, how do you think that affects things? Well, hopefully you realize the more rain you get, the more weathering you're going to get. Okay? Okay, this is a pretty cool chart, and I'll put up a couple of scenarios here that you got to kind of find to figure out what kind of weathering there will be. So the first one, just take a look, right? If it's cold and moist, you'll have a lot of strong frost action. If it's temperate and some moisture, you'll have a mixture there, chemical with physical, right? And if it's all the way on the far end here, you'll have extreme chemical weathering because of a lot of moisture and a lot of heat to speed up those reactions. Now in the tropics, you get a lot of chemical. You still get some physical weathering though, remember, because when you heat something up and cool it down, right, that expansion, contraction, that was a physical thing. So you do get some physical weathering, but obviously mostly chemical. All right, so take a look at this top one. Identify the type of weathering that takes place at a temperature of 20 degrees Celsius. Well, that's here. And 100 centimeters of rain, that's here. So, what kind of weathering do we get? Right, obviously moderate chemical. Try this next one on your own for a second. Right, hit pause. Identify the type of weathering at a temperature of -5 and precipitation of 25. Hit pause and do it. Okay, here we go. -5 and 25 puts you at slight frost action. Okay? And that's how that chart works. Take a look at these children here. These are Inca child sacrifices. Right? Back in the day, the Incas lived South America in the Andes Mountains. And the Andes Mountains where andesite came from. Right? We saw that in the igneous unit. They would, shake and rumble and erupt. And to appease the gods, the Incas would sacrifice their children from time to time. I mean, talk about a commitment and dedication there. My goodness. So anyways, now this happened in 1500 AD. You're talking a long, long time ago, but yet they're still very well preserved. So ask yourself, well, why is that? Why are they so well preserved? Think about the rates of weathering, right? What kind of climate must they have been in to be that well preserved? And if you're thinking cold and dry like frozen, you're on the right track. Okay? Very, very cold and dry. In fact, they brought some of these children down and put them in a museum in South America, and they packed them in dry ice to keep them cold and preserved. I know that sounds eerie and gory, but, keep focused on the climate condition there. All right. The last part, of course, chemical composition of the rock, what it's made of, has a big to do with how fast it weathers. You can see rock A sticking out. It hasn't weathered as much, but B has weathered a lot. So which one is most resistant? The one that's sticking out the most, right? It hasn't broken down as quickly, whereas the least resistant has been weathered down quite a bit. Okay? Rock A, from a picture it's tough to tell what's going on. That's your classic limestone pattern, so that's what that is, a limestone. And B is a shale. Remember, shale is just clay that's compacted, and it breaks into these little skinny pieces very easily. That's what's going on there. Okay, shale is very soft. Okay, a couple other notes. Make sure you get them in there. Composition, depending upon what it's made of. So the harder the mineral, such as quartz, for example, is a 7. It's going to be more resistant to weathering, whereas if something is made with talc and sulfur, right, they're a 1 and 2 on Mohs scale, well, then they're going to break down much faster. Okay? Okay. And of course, ultimately, this will all turn into, remember your breakdown there, you got boulders, cobbles, pebbles, sand, silt, clay. Well, if you start to mix organic matter in with the smaller sediments, you start to make soils. And they call these soil horizons. So you start with solid bedrock, in this case a limestone pattern. You break it down a little bit into, the particles we talked about. Add organic matter over time, and you start to make soil. And that's what's going on there. Soil is the end product of weathering that develops by biologic activity, but of course also the physical and chemical weatherings. Put it all together, and you get eventually a dark, rich soil. If you ever tried doing any planting, flowers, vegetables, trees, whatever you want to grow, you want a nice dark, rich soil that has a mixture of organic and inorganic materials. Okay? Okay. Obviously, the more time you have, the more distinct and developed the soil will be. All right. So you guys have some summary questions relating to weathering and the rates of weathering. Do your best, and we'll go through them in the meet. See you there.